Before I have you practice a few problems on your own, I'd like to look at a connection between the average velocity and the graph of the position function. So I'm going to have you go back a page to where we first found the average velocity of the rock on the interval from 1 to 3 seconds. So we're going to come back up to that graph. And so what I've done is I've drawn a point, 180, that's the ordered pair corresponding to t equals 1 second. And I drew another point, 3, 128, and that's the ordered pair corresponding to t equals 3. And so what we had done before, when we found the average velocity, we used the formula. And so when we use that average velocity formula, s of t sub 2 minus s of t sub 1 over t sub 2 minus t sub 1, we took basically the numerator is the change in y and the denominator is the change in x. So I've drawn a line through those 2 points, and just take a second, pause the video, and think about what that 24 feet per second, or what this formula also represents with respect to that line. Alright, so if this is the change in s sub t sub 2 minus s sub t sub 1, that's actually the change in y, and the denominator would be, if we just refer to this as x's and y's, that would be like the change in x. And so change in y over change in x is actually the formula for slope. So what we've actually found, this is called a secant line. Right, this line right here that hits the curve in 2 places is a secant line. So graphically, what this average velocity represents is the slope of the secant line through those 2 t values, through your endpoints of your interval. And so when I start to let t2 approach t sub 1 and letting those increments get smaller and smaller and smaller, I am approaching another type of line, and that line is called the tangent line. So I'm going to have you scroll down to the last page, or second, well, not the last page, but the page with the tangent versus secant lines. And there's a nice interactive figure here. Let's first just read this. The slopes of the secant lines approach the slope of the tangent line. The secant line approaches the tangent line. So when we let our t values get smaller and smaller and approach 1, our secant line is actually going to approach a tangent line, and this interactive figure helps quite a bit. So I'm going to open up this interactive figure. Alright, so if I slide the t, the time, this is a little slider up here, we can slide that back and forth, slide that all the way to the right. And so on this particular graph, it's the same function that we have, but the graph only goes out to 2.5. So we've got the secant line through 180 and 2.5, 140, and the slope of that secant line is 40. And that is the average rate of change, or the average velocity on that interval from 1 to 2.5. As we slide and we let the 2.5 get closer and closer to 1, I start to slide that back. So now, say we get around 2, close but not quite. So I'm letting my, now I have 1 and 80, and I've got 1.99 and around 128. At 2 it was exactly 128, but the slider is a little difficult to get it on an exact value. So I'm making my interval smaller. I still have a secant line, and the slope of that secant line is the average velocity on the interval from 1 to 2. So as I slide my t sub 2 value towards t sub 1, which in this case is 1, each time I move that and I make the interval smaller, I'm getting a new secant line, in which case I'm getting a new slope, and that slope is representing the average velocity. This red line is called a tangent line, and just one of the simpler definitions of a tangent line is just a line that touches a graph at one point. We will talk more about tangent lines and get a more elaborate definition in later units. But what's happening here, again, as I make that interval smaller and smaller, and I'm letting t sub 2 approach 1, my secant lines are starting to approach the tangent line. And so the slope of the tangent line will be represented by the instantaneous rate of change, whereas the slope of the secant line is an average rate of change. We will revisit this idea of the limit of secant lines as t sub 2 approaches t sub 1 approaching a tangent line. We'll revisit this idea when we start talking about the derivative. For now, I'd like you to just do two problems. Pause the video first and work these two problems out, and then start the video again to check your work. Alright, for practice problem 1, the function s of t represents the position in feet above the ground of an object at time t in seconds moving along a vertical line. Suppose s of 2 equals 140 and s of 4 equals 155. Find the average velocity of the object over the time interval 2, 4. So we'll start by writing down the formula for average velocity. Now we'll fill in the values. S of t sub 2 is 155. S of t sub 1, which is s of 2, is 140. And all over t sub 2, which is 1, minus t sub 1, which is 2. Alright, working out the arithmetic, we get the average velocity to equal 7.5 feet per second. That would be the average velocity over the time interval from t equals 2 to t equals 4, so over that 2-second interval. Okay, the next problem. Consider the position function s of t equals negative 4.9 t squared plus 30t plus 20. Complete the following table with the appropriate average velocities, then make a conjecture about the value of the instantaneous velocity at t equals 2. So the first thing I'm going to do is put the s of t in my calculator. Once you put your function in to the y equals, you want to set up your table. Make sure your table is set up as ask and auto. We want the independent variable, which is your t, on ask, and the dependent variable on auto. And again, what this does is when you feed it a t value, it gives you the s of t value. Once you set up your table, it should be all set unless you've used it for something else. We'll go to second graph, which is the actual table, and we'll plug the various values in that we need. The 3, the 2.5, so 3, 2.5, 2.1, 2.001, and I'm going to add one extra value, which is 2.0001. I'm going to transfer these values so I can use them in the formula for average velocity. So writing down all of the values for the s of t sub 2's along with the value of s of t sub 1, and then plugging those values into the formula v average equals s of t sub 2 minus s of t sub 1 over t sub 2 minus t sub 1 gives us these average velocities. And you can see initially when I set up this table, I actually stopped at the interval 2 to 2.001, and I wasn't confident in the value that I was approaching in the actual limit. And so I added another interval, 2 to 2.0001, and then I could see here that I am actually approaching approximately 10.4. So the average velocity is approaching what we call the instantaneous velocity, which appears to be 10.4. Again, in a later unit, we're going to find an analytical way, not just a numerical way, but an analytical way of actually finding the instantaneous velocity. So our conjecture is that the instantaneous velocity is approximately 10.4 feet per second. So I didn't show all of the work in plugging all these values into this formula, and it does get very tedious doing that repetitively. There is a shorter way using your calculator, and I'd like to show you that now. And you really have a choice of using this shortcut or doing it out by hand. Not everyone feels confident using the shortcut